So it's 1:45. Welcome, everyone. I'm sorry for the issue with the link today. There seems to be an issue with WebEx, I think, and it somehow changed the link in the middle. But I'm glad you could make it. And if you have anyone else interested in joining, please also send them the new link so that they can join the seminar. In any case, it's being recorded, will be uploaded to the website, so you can always watch it again later. But it's always good to have you live with us and contributing to our discussion. So it's my pleasure today to introduce to you Vladimir Spielmann from BFS. Vladimir studied physics at the Ludwig Maximilian University in Munich, and then studied medical physics at the Technical University of Kaiserslautern. He then worked a bit as a research associate at the Helmholtz Zentrum here in Munich, and then received his doctorate in 2016 from the Otto von Guericke University in Magdeburg. And here he worked on the topic of uncertainty and sensitivity analysis of administered doses and investigations into the biokinetics of incorporated radionuclides in the field of nuclear medicine. He currently works at the Federal Office for Radiation Protection in the field of internal dosimetry and biokinetic modeling. And today his presentation will be on dose coefficients for chronic intake of radon gas and progeny by children. So Vladimir, the floor is yours.
Thank you, Warren, for your introduction. So as Warren said, the topic of the research seminar is dose coefficients for chronic intake of radon gas and progeny by children. So somewhat to background, brain consists mostly of 60% of fat. Radon gas is soluble in lipids and tends to accumulate in fatty tissue, like brain tissue. The only demonstrated association related to radon exposure is lung cancer. It's proven that we have here a relationship between radon exposure and lung cancer. However, gas exposure could cause other diseases like Alzheimer or leukemia or brain tumors. So the question is there a relationship between radon exposure and brain tumor? To try to answer this question, improvements in brain dosimetry is needed. We have to calculate dose coefficient in more precise way to reduce the uncertainty. How do we calculate absorbed dose? We are using ICIP or MET formalism. That means if radionuclides or radioactivity is inhaled in human body, it's deposited in different regions of the human body. And to describe the kinetic in the human body, we are using biokinetic models for different regions of the human body. Here you see some biokinetic models of ICIP for respiratory tract, for alimentary tract, but also for systemic model, for all systemic organs, including blood pool. In these biokinetic models, we are using compartments. If the radioactivity is deposited in these compartments, we say these compartments are source organs because these organs are sources of activity. So these compartments are connected to each other via transfer coefficients. These are lambdas here. And mathematically, if you want to describe the kinetic in the human body, you have to solve a system of differential equations. This is a first order kinetic, what we have here. The solving of the system of differential equation gives you time activity curves in each compartment, in each source organ. After integration, if you want to determine the area under the curve, you can calculate time integrated activity. This is a whole number of disintegrations in the source organs. What else we do need to calculate absorbed dose? We have a dosimetric part. With the help of Monte Carlo simulation and, for example, voxelized phantoms, we can calculate absorbed fractions of energy that is emitted by source organs and is absorbed by target organs. So if you multiply these absorbed fractions of energy by the type of energy and yield of energy and divide it by the mass of the target organ, you can calculate so-called S values. Together with time-integrated activity, we can calculate an absorbed dose in a target organ. So absorbed dose in a target organ is a product of the time-integrated activity, or the whole number of disintegration in the source organ, and the S value. In our case, we have radon gas. We inhale radon gas, and if we inhale radon gas, we inhale also radon progeny. We have also radon progeny in the air. We are speaking about radon progeny. That means radon progeny that it's created outside of the body in the air. So we inhale radon gas and radon progeny together. This is a mixture in the air of radon progeny and radon gas. Radon progeny could be in unattached form or in attached form. Unattached progeny could attach to aerosol particles and build clusters of different sizes. In general, we say we have a log normal distribution that is trimodal. That means we have a log normal distribution with 3 different median values. We're speaking about nucleation mode if the particle sizes are between 10 and 100 nanometers. We're speaking about accumulation mode if the particle sizes are between 100 and 450 nanometers. And for large particles larger than 1 micrometer, we say we have a coarse mode. So we have a mixture of progeny of these different modes in the air. And that means with the aerosol parameters like median value of the log normal distribution or standard deviation of the log normal distribution or particle density shape factor, we can calculate depositions in the respiratory tract, different depositions. Here's a dependency of particle sizes on the deposition in respiratory tract. You see smaller particles tend to accumulate in upper regions of the respiratory tract, and larger particles tend to accumulate in oral cavity or nasal cavity in upper part of the respiratory tract. Together with breathing rates and time budgets, how the person spends the time, the day, with the help of dosimetric models, we can calculate the dose coefficients, dose per activity. But there are some more parameters, for example, anatomical and physiological parameters. ICRP defines anatomical and physiological parameters for 6 reference ages. For newborn child, 1-year-old child, 5, 10, 15, and adult. What we need are dose per exposure, because what we know is exposure of radon gas or radon progeny in the air, and what we want to calculate is absorbed dose to brain or to other organs. So what we have to know are dose per exposure, dose coefficients. For these purposes, we have to know some other parameters like unattached or attached fractions, activity ratios for different isotopes of the chain. What is the ratio from polonium to lead, from lead to bismuth? We have to know the equilibrium factor. How far away are we from the equilibrium between radon gas and radon progeny? Breathing rates. These all parameters are needed to make this conversion from dose per activity to dose per exposure. So, as I said, ICRP defines anatomical and physiological parameters for only 6 reference ages. What we did, we divided the time interval between 0 and 20 years in 130 different time intervals to calculate dose coefficients for 130 ages. For this purposes, we divided the interval in 130 intervals and calculated intermediate values for each parameter. So we have here 130 parameters. And from this 130 parameters for 130 ages, we calculated 130 different depositions for attached and unattached modes. Here are some more interpolated parameters like transfer rates or volume of respiratory tract airspace or breathing rates. That means up until now, we had only 6 reference ages from ICRP with 6 intakes. That means if you consider children between 2 years and 7 years, you had to use those coefficients from a 5-year-old child. We have here only 6 intakes, only 6 ages. And what we did, we calculated 130 ages, those coefficients for 130 ages. This is a more better resolution. You see here a comparison of absorbed dose to brain for radon gas and radon progeny. If you compare only 6 intakes, only 6 ages, and 130 intakes, you see for some cases you have an overestimation or underestimation of absorbed dose to brain, depending on the age. This is an example how to calculate dose to brain. If we have a child, and this child was diagnosed with brain cancer as he was 1 year old, the question is, what is the dose the brain received as the child was 0.5 year old? So we have now 130 dose coefficients, but for each age we have 130 dose coefficients. That means we have a matrix with 130 rows for ages, columns for ages, and 130 rows for each interval. We calculated dose coefficient for each interval, for each age. And if you want to know what is the dose the brain received as a child was 0.5 year old, you have to choose the right row, the correct row. This case is row number 13. So the formula is straightforward. You have to know what is the intake of each interval. You have to calculate the intake or exposure for each interval. And you have to multiply this intake by the dose coefficient. And then you have to build a sum. If you want to know what is the dose to the brain received as a child was 1 year old, then you have to choose this row number 14, because 14 means the child is 1 year old. So the general formula is, as I said, quite simple. What you have to know, what you have to calculate is are the intakes or exposure for each interval. And then you have to multiply it by the dose coefficient and have to build a sum over all over the age, all ages. We provided those coefficients separated for male and female, for radon gas and radon progeny. But also we separated those coefficients by different types of energy. It's very helpful, it could be helpful to understand what is the contribution of different types of energy, of alpha energy, of gamma, beta, X-rays, and so on, if calculates the brain dose. Here's a comparison. We calculated these dose coefficients with standard values from ICRP. That means, for example, for equilibrium factor, we say we used an equilibrium factor of 0.4. This is a standard value for indoor workplaces. But if you change this equilibrium factor from 0.4 to 0.6, for example, you will see differences in brain doses. It's depending on age. The same for unattached fraction, for example. If you change the unattached fraction from 0.1 to 0.08, you will see also here small differences. Or time budget, from indoor to outdoor, also here you will see differences. That means we calculated and provided dose coefficient for standard values, but we could calculate also other dose coefficient for special scenarios. So we calculated this dose coefficient and asked what else we can do to improve brain dosimetry. A big topic, a big discussion was about pathways of radon gas and progeny to the brain. In health, radon gas and radon progeny can pass the blood-brain barrier, but ultrafine particles smaller than 100 nanometer, can reach the brain both via the systemic blood circulation, but also via the olfactory neuronal pathway. That means if there are ultrafine particles in the nose cavity, then can reach the brain directly via the olfactory bulb. We didn't find much information in the literature about this topic, especially for radon progeny. The big question is if radon progeny could reach brain via the olfactory neuronal pathway. Because theoretically, yes, unattached fraction could reach nucleation mode where the particles are smaller than 100 nanometer. Theoretically, they could reach brain via olfactory bulb. But we have to clarify this. We have to we make now literature review and try to clarify this topic. But what we did something else. We looked at the biokinetic model of radon gas. At the left side, you see the biokinetic model of radon gas, the standard model from ICRP. And as you can see, you see no brain compartment in this model. Brain is included to other compartment with all other organs. You see here kidneys, liver, red marrow, but all other compartments or source organs are included in other compartment, also brain. That means the brain is treated in the same way as all other organs from the compartment other. So what we did, we added this compartment, brain compartment, to the model and calculated transfer coefficients from arterial blood to brain, from brain to venous blood, but also we recalculated transfer coefficients from blood to other, from other to liver, from liver to blood. If you want to calculate such transfer coefficients, especially for radon gas, you have to use Fick's law of diffusion. That means what we have to know are such parameters like blood flow rate through the systemic tissue. This is a percentage of cardiac output, or partition coefficients of organ. This is a relative solubility of radon in tissue and blood, or also volume of tissue or blood is needed too. So we use these parameters to calculate transfer coefficients for blood to brain to this new added compartment. At the right side, you see a table from ICRP with partition coefficients for radon, xenon, and krypton. And you can compare here partition coefficients for muscle and for brain. Muscle is the same as other because other mostly consist of muscle. So if you see the partition coefficient for radon for muscle is 0.36, but for the brain it's much larger, 0.72. Such tables or such values you can find also in other literature, in other papers. So we use these partition coefficients for brain of 0.72 and calculated the brain dose with this modified model again. And what we saw, we have an increase in brain dose depending on different ages. For newborn child, we have an increase in brain dose of about 10%. But for other ages, from 1-year-old child to adult, we have an increase in brain dose of almost 100%. At the left side, you see parameters we use by this calculation. Of course, for partition coefficients, we used a larger value of 0.72. What I found also in the literature, the information about blood flow rates to brain for different ages. We have a standard value of 12% for adult and for newborn, but for other ages between 1 year and 15 years, these parameters are larger, between 13 and 20. I used also these parameters and make the new calculation of brain dose. And I saw that we have also here an increase in brain dose of almost 1%. So the brain dose is not very sensitive according to this parameter, but nevertheless, also here we see an increase in brain dose. Okay, here's some more comparisons. You see here a brain dose compared to other organs. You see the brain dose is quite small compared to other organs. At the left, you see unmodified model, the standard model of ICRP. But if you modify the model and calculate the brain dose with the partition coefficients of 0.72, you will see the much bigger brain doses. Now it's comparable to other organs, for example, to thyroid. Last but not least, a very important point, the heterogeneous distribution of radioactivity in brain. Our assumption is always we have a homogeneous distribution of radioactivity in each compartment, in each source organ. But it could be very important to say the distribution of radioactivity in the brain is not homogeneous, because some subregions of the brain could consist of more fat, like white matter, for example. So brain dosimetry could be improved by dividing the brain into subregions with potentially different radionuclide concentrations. We can do it, of course, if we find some information in the literature. We can do it for biokinetic models, but we need corresponding absorbed fractions. It means we have to make Monte Carlo simulation to divide brain in different subregions and calculate absorbed fractions for these subregions. There are some papers, some publications in internet from MERT, for example, or a publication from 2004 where they did it. They made this Monte Carlo simulation and divided brain in different subregions. Maybe we could use these specific absorbed fractions and to investigate this point. But as I said, this is more for the future. Okay, then I have to conclude. We calculated dose coefficient in more precise way for 130 ages. We used standard values from ICRP, but we can do the calculation also for all other possible parameters. We modified the biokinetic model of radon gas. We added a brain compartment, and we saw an increase in brain dose up to 95% with this modified model. The topic about olfactorial neuronal pathway, we have to investigate it. We have to make more literature review. We need more information, more data about this topic, but it could be very important. And the last point is the heterogeneity in the radioactivity distributions. It could be also very important and could become decisive in improving brain dosimetry. Thank you for your attention. If you have questions, I try to answer your questions.